all good. Yay. I'm going to close the door. Okay, so today I'm going to deviate a bit from the order that the paper is written in. And what we'll do is we'll directly look at the impossibility of deterministic schemes, because we've not really done any proofs so far. So let's actually prove this. So this is section 3 in the book, in the paper. It's the impossibility. Don't even need that actually. It's just impossibility of deterministic schemes.
What does it mean? So, previously the randomness.
Yeah, I'll formalize what I mean by a deterministic scheme. There is, of course, like, something needs to be said, right? It's not clear what deterministic means. Okay. So let's define deterministic schemes first, otherwise Uttam will get upset. So here's the definition. All of this is, of course, in the context of uncloneable encryption, right? So, okay. So an encryption scheme that we normally write as gen enctech. Okay. So is a deterministic scheme if the following hold. So enc can be realized as a unitary matrix U sub sk. Okay, where sk is the secret key coming from the gen algorithm. It's sort of a semi-formal definition, acting on the plain text or the message, plain text / message register M. Okay, and some auxiliary qubits initialized to 0. Okay, resulting in a pure state ciphertext which we write as C sub sk, okay, of length lambda. Okay, is the definition okay?
But for example, you are allowing auxiliary qubits.
Yeah, initialized to 0.
So what stops that, so USK acts on only M or on the everything?
Or on both, yeah, acting on this and
this is always possible, right? So whatever so any channel that I will have, I can realize on bigger subspace as unitary.
but you will have to trace out something. Here we're not allowing to trace out anything, so you get the entire output as the pure state.
Okay, and 0 okay, so the initialization is also known.
Yeah, initialization is fixed, so you don't have randomness there. Other than, of course, sk, so you can have some randomness in sk, but okay, and then so there's no randomness in addition to what was generated in the gen procedure. That's the key. Like enc is not using some private randomness in addition. Okay, and then dec is just U sk dagger and then measure. In computational basis. Okay. Uh-oh. Okay, I think I messed up my notes. After page 53, I have page 56.
And
Okay,
you
got
say
it.
length explicitly lambda, not poly lambda.
Yeah, I mean, these guys are a little bit, I mean, this paper is not as sharply written as I would have liked, so I guess you could adjust it. It's not. Yeah.
Also, the number of auxiliary qubits you didn't say what, and total length is lambda. So the message is not of length lambda.
Yeah, so lambda is a security parameter. So you always take lambda to be independent of the message length. You can always, not always, but typically you're doing asymptotics. You're taking lambda tending to infinity and so on, right? So you're thinking of a fixed message length and scaling the security parameter.
I see.
Like you might not use all of lambda. Like for example, in the one-time pad, it suffices to just use the length of the message, but in general, you're allowed to. Okay. So far, we haven't said too much. Okay. So now let's say a few things about this. So the first is that correctness is kind of by construction, right? By definition, essentially, right? Because you're playing U-dagger, so nothing fancy there. Let's look at two examples. Okay, so the first one is suppose SK encodes, a description of two orthogonal states. Phi 0, phi 1, right? Okay, and a message is mapped, a message M, let's say a message B is mapped to phi sub B. Okay, so this is an example of a deterministic scheme. So you have the secret key basically tells you which two orthogonal vectors to use. Okay, and then the encryption is that whatever message you get, you encrypt it as the first vector or the second vector. Okay, it's a very simple example of what.
And here the length of this phi 0, I mean, how many qubits are there?
That can depend on the security parameter, because you can scale SK with lambda, so the description can get more involved. Yeah. Okay, so that's the first simple example. Second one's more fun, which is the conjugate encryption scheme that we saw in the last paper. So conjugate encryption from Broadbent and Lord, not Lloyd. Right. So gen 1 to the lambda is going to output SK, which was just R theta, where R and theta was sampled from 0, 1 to the n. Okay. Then enc SK comma M is the following. So you XOR the message with little r, and then you apply h to the theta, which we write as, you remember this notation, right? So x to the theta was h to theta x. So using that notation here. Okay.
So here n is like lambda, right?
Yeah. Okay. And then decrypt is, it'll take the secret key, it'll take row. Okay, and the secret key is this theta. Okay, and it computes rho prime, right, which is just applying h theta, and then you can measure it to obtain this the string C, and then you return C XOR with little r, okay, as the message frame. Okay, so this example was more interesting, right, because it looked like there was some potential for it to be unclonable, right? It looked like if I give you the encryption and you don't have information about theta and r, it's hard to split it into two, right, such that both of them. So it looks like this might actually work, but this is also an example of a deterministic scheme, right, because you see the encryption procedure is just a unitary that depends on the secret key, right? It's not doing anything much beyond that.
Sorry, what is this language m plus r power theta?
Yeah, because that's a part of SK, right? So SK gives you information about r and theta, and then it's just, sorry, what was your question?
What is the
Notation? It's over there.
Okay, so you
It's just Hadamard's, yeah. Yeah, I can write it explicitly, it's probably better. Doesn't cost much.
And here method is length n.
Here, yeah, this is something they don't say very clearly, but I'm guessing yes. Let's say the message is length m.
And what is rho? Rho is this state.
Yeah, rho is whatever you received as the input to decrypt.
That will be this encrypted thing.
Supposed to be, yes.
Oh, okay, because that depends on rho. So whatever you will get rho prime at the end.
Yeah, maybe I should write sigma. Maybe no, it's fine, right? It's rho. You do something, you'll get rho prime. You measure to get C prime. Okay. Okay, so the thing is that these guys already showed. So they showed that it doesn't satisfy. Okay, so let me write it separately. So BL20 already showed their scheme cannot satisfy unclonable int CPA. Oh no, I didn't define int CPA for you guys because I skipped the order. Okay, so maybe I should define it. Okay. Let me complete the remark.
Trojan plain text you told in the beginning, right?
Yeah, but this is unclonable int CPA. So it's so I'll define it in just a moment. For the moment, just think of it as unclonable indistinguishability for the purposes of this remark. I'll define what it means. Okay. So that it cannot satisfy this thing, and here, okay, so here we show like here it follows from the general theorem. Or basically here they rule out a larger class essentially. So rule out a larger class. Okay, so it's basically a generalization. And the idea is kind of cute. Okay, so for int CPA, maybe I should actually define it first. I'm trying to see where I put it. Okay, let's actually carry on. I'll define it when I'm defining the attack. It'll show up in just a minute. Okay, so I'll define it when I define the game. So we'll see it then. I don't think it's worth because they actually don't use the CPA property. They show it already at the indistinguishability level. So we don't really need to. We'll do it later. Okay. So the theorem now is the following. So they prove that for any deterministic scheme, there exists a universal unbounded adversary A, B, C. Okay. What is going on? I'm messing up the order of my notes, is it? Yeah, I think I skipped too many things. I'm sorry. Yeah, I think I skipped a bunch of preliminaries, so it kind of messed things up a bit. But okay. Yeah, I'm sorry about this, you guys. So the advantage when A, B, C are playing the security game, okay, this is always going to be greater than 0.568 as lambda tends to infinity. Okay, and the security game is the int CPA game, where we don't really need the CPA part. Okay, so when we do the proof, we'll see exactly what's going on. Okay. There are two small things that are worth mentioning. One is that their proof does not work if enc somehow uses additional randomness. Okay, and we already know that deterministic schemes will not work with multiple encryptions, right? Like for example, if you encrypt twice using the one-time pad, then you already start learning things, right? So we know that you do need some randomness already for non-trivial things. But the thing is that their proof technique does not work if you have any kind of randomness in enc, or if you do not give the entire ciphertext. Okay, and we'll see why it doesn't work. So that's one of the open questions, to see if one can actually extend the impossibility to this regime. Okay, if one of you is interested in thinking about it. Or to prove a counterexample, actually, to construct a scheme. But we don't have any construction in the plain model, so you would solve two problems at once if you solve it. Okay, so that's what the remark was. I'm not going to write this. I think we can skip that part.
So in BL20 there was no random override.
Sorry, say it again?
BL20 there was no random override.
Yeah, that's the point. These are schemes in the plain model, and they're trying to show the limitations. So the thing is, in their paper, they had to use a random oracle, and they're justifying why they had to use a random oracle. So they are saying that you cannot construct information theoretically secure schemes, while they are able to construct information theoretically secure schemes. Okay. Alrighty. So now we're going to collect some background for doing the proof. So we'll look at some lemmas or whatever about the Ha measure, which I also don't know much about, but I just think of it as a uniform measure. So let's do that. Okay. Preliminaries on the Haar measure. Alrighty. So here's the notation we use. So mu n is the uniform spherical measure on the unit sphere C2 tensor n. Okay, and eta n is the Haar measure on the unitary group. Is it just me or it's actually warm here? Normally it's colder, no?
Yeah, today it's not very cold.
Okay.
You can ask the guy there.
It's okay. Is the AC not working?
AC are on, the one last one is on.
There's a remote, he's saying. Where's the remote? Oh, you see the remote over there. Yeah, can you see if you can drop the temperature maybe over? Okay, good. Thank you. Okay, so uniform spherical measure is fine, right? It's just saying that you pick a vector uniformly from all unit vectors. So that's fine, right? The Haar measure is basically saying, you can think of the Haar measure as basically picking a unitary uniformly from the set of unitaries. So it's basically invariant under permutations of qubits or whatever.
These are usually equal, so what is uniform spherical measure?
Oh, this is, you're sampling a vector, here you're sampling a unitary.
They both are equivalent in the sense that if you want to generate a pure state, you can apply.
You have to, like there are theorems, I think you have to prove
Sure,
things.
sure, I'm just
Yeah.
trying to understand. So if I think of it as 1 over the total number of vectors, then mu1 is 0, right?
Then what is 0?
So uniform spherical measure, you said that so there are like many vectors on this sphere, and the uniform will mean that I will pick one randomly. So the probability should be proportional to 1 over the number of vectors there.
Yeah, so it would be like a measure, right? Like that's true for any continuous measure, right? Like the probability, like if you have an interval, right, from 0 to 1, and you uniformly pick a number, the probability of picking any one exact number would be 0, of course. Yeah.
Yes.
But that doesn't mean the measure is ill-defined, right? The measure is still fine, it's uniform.
So what
I
is the
don't
probability that I will associate with picking one number in this case?
0. You always think of intervals. You don't think of.
Okay, so there we will talk about intervals.
Well, whatever they will, but yeah, the uniform measure is well defined regardless of how you think about it. Right? Okay. Okay. So yeah, so far we haven't done anything. Have you guys seen the Haar measure before? In of course you have. Okay, good. But don't worry, we won't need too much. Okay, it'll mostly be intuitive. So we'll see where we need to use that argument once that it's uniform. So we'll see where it comes. Okay. Here's a lemma that relates the Haar measure to this. The argument is actually extremely straightforward. You'll see. There's nothing very deep happening here. Of course, once you know the argument. So let f be a function from C2 tensor n cross S C2 tensor n to R. Okay. Then for any two fixed vectors, so basically going from two unit vectors to a real number. Okay. So you can think of it as, for example, an inner product does this, right? You give it two vectors and it gives you a number. So you can think of it that way. Okay, so if you're for any two fixed vectors, phi 0, phi 1 in S, C2 tensor n. So you take any two unit vectors that are orthogonal such that phi 0, phi 1, the inner product disappears. So for these vectors, it holds that which is I think what Uttam Bhai was also saying. So if you take the expectation of unitaries taken from the Haar measure, okay, so it's U acting on phi 0 and U acting on phi 1, sorry. Okay, so this function acting on the vectors that you fixed, which are orthogonal, you apply the unitary U. It's going to be the same as, so you apply a Haar unitary. Is this the same as just picking Haar vectors that are orthogonal from the, and then you have psi 0 psi 1 equals 0. Okay. Is the statement okay? Yeah, yeah. F is any function that is defined on 2 unit vectors, like which maps 2 unit vectors to a real number. Then you fix any 2 vectors, apply the Haar measure, sorry, the Haar unitary. Then the value of f on average would be the same as the value of f if you took 2 vectors from the uniform measure on the sphere, which are orthogonal. Right? So that's all this is saying. Okay, so that's not very surprising. That's strange. It's intuitive, right? Because
all phi 0 phi 1, this is what is bothering. So there is something that I don't understand about spherical measure.
phi 0 phi 1 are orthogonal.
Yeah, I'm saying that this should be true for all phi 0 phi 1.
Are not just orthogonal ones.
Exactly, because this means that I'm not understanding spherical measure. Because you
No, I think the statement, it probably is true. I also had the same doubt. I also thought it's probably true in general, but I think they're showing that even if you have the restriction, it's true. But yeah, maybe you're right. I don't know. If it's in general, then it's. Yeah, yeah. I agree. There is some subtlety. I agree. Because the intuition is that you take 2 vectors and you rotate them in some weird way. It's the same as just picking those vectors and then imposing the constraint. Right? But somehow something extra is happening, which I don't know.
Exactly, because if you change the angle, your argument is still works.
Yeah, exactly. My argument is independent of the fact that they're orthogonal, so I'm missing something, of course. Okay, so I don't know the proof of this. It's in. There are some lecture notes by Watrous on the Haar measure. We can do that, but I think it'll take a lot of time, and it's not really needed for the proof. I think these things are kind of enough. Okay, good. And now, okay, so now we look at what is called Levy's lemma. I have a feeling we'll be able to complete the proof today, which is very nice. Which is the counterpart of the Chernoff bound. But on the uniform spherical measure. Okay, so what is the statement? So the statement is the following. This is Levy's lemma. So it says let f be a function from spherical vector to a real number. Okay. Satisfying that f phi minus f psi is at most kappa times phi minus psi 2 norm. for some fixed okay. So this function is taking phi, producing a number, and you're looking at the norm of that number, and this is at most kappa times the distance between the okay. So suppose you're given such a function, then there exists a universal constant delta greater than 0 such that for all epsilon greater than 0, the probability that you sample psi, the probability over sampling psi from the, which one is it? The uniform spherical measure. Okay, and this is the kind of tail bound sort of thing, right? So it says you take f, you evaluate it on psi, where psi was sampled from the spherical measure, okay? And you take expectation and subtract it from the mean essentially. So you take the mean of this same function. Okay, so you take the expectation, subtract it from this f psi, and ask how far is it from this mean. Okay, so is it the probability that it's epsilon far from the mean? Okay, is going to be bounded by 3 times minus delta epsilon 2 to the n by kappa square. Okay, so it's very much like a Chernoff bound, right? Like it says that the probability that you're away from the average exponentially decays, right? So that's what this statement is saying, but it's now saying it for this.
Power n in the power.
Yeah, at least that's what I wrote, because I think it is the dimension of the vector space, right? I guess there are n vectors, so it's 2 to the n. This is the dimension. So it's probably scaling with the dimension, which is probably okay. Okay, good. Okay, and the final thing we'll need, so these are just the 3 technical statements, the ingredients we'll need. These 2 are standard, I think. This last one is not standard, but we'll not do the proof unfortunately today, maybe later. Okay, so the following is from a paper by shoot. That's the thing with printing things and not the references. I don't know what MZB is. I couldn't click on it, so maybe you'll see the paper. I'm guessing Z is Andy, but I don't know what M and B are, which is not nice. Okay, so sorry about that. Okay, so the following is from and plays an important role. So it's crucial, and it's crucial here. And what is the statement? The statement is kind of cute. So I'll ask you to guess what the statement is, okay? So let me set up the premise, and I'll ask you what you guess the answer should be. So suppose that psi 1 and psi 2 are unit vectors, okay? Sorry, but in registers of 2n qubits, okay? So suppose these are independently sampled. Yeah, I mean, I don't know why they write it like this, okay? Properly, okay, so these things are sampled from mu to n, okay? And so obviously they belong to S C2 tensor to n. Okay, so they're sampled from the uniform spherical measure, 2 vectors. And you define rho 1, rho 2 to be the corresponding density matrix on the first n qubits. right? So you sampled a big vector, you're taking half of it, you're looking at the density matrix, and the statement is that as n tends to infinity, the trace distance between rho 1 rho 2 almost surely, so there's some probabilistic, converges to, okay, what do you think the answer is? Is it close to 1? Is it close to half? What do you think? So you took two random vectors. No, but if it's randomly chosen, right, it would be identity, right, mostly.
Both of them will be identity.
Right.
So the distance will be 0.
But yeah, so but it's a finite thing, right? So it's not.
But you take the dimension to be very large.
Yeah, so I guess there will be some dependence on n. Like I think asymptotically, because you're always taking half. It's not like you know.
So that is the result, right? If you pick a pure state on larger subspace and trace out the part, then you will get maximally mixed state. And both of them will give you maximally mixed. But your bound is very weak because there is factor of 2 to the n there. So this leaves. Oh no, I am not using that.
Yeah, you're not using that. Yeah, that's
I mean, I am using that to say that rho 1 is maximally mixed. So without Levy's lemma, you cannot say that rho is maximally mixed.
I see. Okay, that proof I don't know. Okay, I'll ask you later.
Anyway, so what is that? Is that?
Yes, it turns out that this is. So this converges to a quarter plus 1 by pi for some reason, which is 0.568. Okay, and it turns out that this is the advantage that we will get in the construction. It's going to be constant. Okay, so the trace distance between rho 1 rho 2 almost surely, okay, converges to this as yeah, so we already said as n tends to infinity. Okay, good.
So what would you have argued? Like,
Oh, I have no idea. I don't know the proof. I was just asking if you have any.
You said that you will ask us to guess. So what would you have said?
Oh yeah, I probably would have also said 0, right? Like because I thought that it should be mixed, but it's. I think the point is that you're not. You're always taking half of the vector. It's not like you take fixed number of qubits and then the vector is getting larger and larger. No, as the vector is getting larger, the density matrix is also getting larger. So you always have half the density matrix. So maybe that's why. If perhaps you took a vector that scales with n, but you looked at say only some constant many qubits that doesn't depend on n, then maybe it would become 0. But as it's stated, it doesn't.
And when they are saying almost surely, probably they are computing the probability that trace distance becomes this number. So you can compute the average of trace distance because.
Yeah, this will probably be with like 1 minus negligible, something like this.
Right. So
This.
they probably are using them if they want to claim this.
Right. Yeah, I don't know the proof. Yeah, this is something.
If you just use random coin tosses instead of like density matrices, then we would expect it to go to 0, right?
So if instead of the vector, this is a statement of the vector and the density matrix. So I don't know how you're fitting in the random coins. So how are you fitting the random coins?
Like I was just thinking of
You start with the density matrix.
you like have 2n tosses.
So you're starting with the density matrix,
Yeah.
essentially, and then you're removing
Like
part of the
density
density.
matrix that is just classic.
Yeah, yeah.
So how will
So
you
if
do
you-
by tossing point this rho 1 rho 2?
It's just diagonals, I guess. You
Yeah,
just
just
pick the entries. But it's already a distribution, so.
Normalize it, right? So
Okay. Let's not get distracted, unless there's a crisp argument. But yeah, there's something worth checking.
Go to the side here, this element,
That MZB 16.
and that is recent. Like 16 is recent.
It's about 10 years now. We're getting old.
Yes. Always recent.
But I don't know. Yeah, as far as math results go, yeah, I guess it's very.
It kills a lot of my intuition.
You should check it. It could be wrong. Sometimes these things are wrong, so it might break things. It's unlikely. Xandy doesn't get them wrong. He just doesn't write them very well, but
I mean,
doesn't get them wrong. Yeah, I don't know of any Xandy paper that went. Actually, there was some mistake in one of the papers, but the result was still correct.
This will be close also. It will not be a mistake.
Right. No, but then this is, yeah, the point is that the attack that they give, which I'll describe in just a moment, essentially would produce an advantage which is exactly this number, 0.568. So it's important that it's correct, or at least that it's greater than half. That's important. Okay, now there's some notation. So this E psi is.
Sorry. So as I remember, this result,
Mhm.
this result is based on Levy's lemma, and
This result is which? Theorem 2.5?
Yeah.
Oh, okay.
TD will depend on Levy's lemma, and Levy's lemma's convergence depends on K, this K factor, ellipsis constant. And if K is bad, so for example, if K turns out 2 to the n by 2, then it will not converge to 0, this probability. But if you, instead of choosing C2 tensor 2n, you have chosen C2 tensor m times n, okay, and then take n to be large, then it will go to 0. Here m and n are equal, so that is why I was.
No, I think I got lost. C2 m C2 tensor m times n.
Psi1 psi2 in 2n dimensional 2n qubits on
Okay.
2n qubits. Instead, if I have chosen an mn qubits,
Okay.
and then I trace out n part where I assume that m is less than n.
Yeah,
Then
sure.
it will go to 0.
I see. So that's, you were checking your intuition that it checks out.
So since they are same, so this k square will.
I see.
So it will not converge to 0. It will converge to something else.
I see.
Because you see that
Makes
this
sense. Okay.
K will depend on what you are doing.
How much you're throwing away, right?
Yes,
K would basically. Yeah, okay, got it. Okay, good. So
if you look at Andreas Winter's paper, you students, like there's paper called Aspects of Generic Entanglement, where they compute this quantity, and they saw that it will go to 0, but only when I said that was assumed.
yeah. So I think the idea is just that how much of the vector you're throwing away. That's crucial. So if you're throwing away only half the vector, then you don't have guarantees of that kind. So they probably have to use some other technique. If you're throwing enough of the vector, I think you can get stronger. Good. Yeah, thank you. I did not notice the connection with the K. Okay, so now some notation now. So expectation over psi is, is just denoting that psi is sampled from, so this is a short for sampling psi from the the spherical measure. Mu was the spherical one, right? I keep confusing. Yeah, thank you. From the corresponding Hilbert space, and then E sub v will be used as short for sampling v from the Haar measure. What was the eta n, right? Probably. Okay. Where n is like the dimension. Okay. Very nice. We're making good progress. I'm happy. So we have all the pieces, lined up, and now we can give the attack. So what's the attack? So this is section 3.2, attack schemes. Okay, so the attack is actually, let me just write the attack here. Okay.
So these are attacks on deterministic.
Yes. I mean, they will probably only work for deterministic schemes. Maybe they also work otherwise, but we don't know. Okay. So, so remember I didn't define NCPA, indistinguishability, unclonable in CPA. So I'm going to implicitly define it here. So here's the adversary A, okay? And the adversary is going to send to the challenger 2 messages. Okay. Doesn't really matter, they just have to be orthogonal. Okay, so they'll just send these two messages, and orthogonal, they just have to be distinct, I guess, at this point. Okay, and you will get CTK. Okay, so the adversary is going to encrypt one of them, right? As we do in the NCP game, we'll send it. Okay.
Also, the length here is again like.
Yeah, we're taking n lambda to be the same for the moment. Yeah.
But there is no ancilla right here because if the because you took ancilla also somewhere in deterministic scheme.
You can take it to be lambda. I think it's probably okay. You can take it to be lambda. You can take it to be lambda. It's okay. Yeah, thanks. Yeah, you can take it to be lambda. I think we'll see if something breaks. Okay, and then A applies Haar unitary, Haar random unitary. Okay, also the K is actually SK. Okay, so this guy is using K and SK interchangeably, and I am also copying the notes and messing it up. So I'll try to use SK, but if you see a stray K, you know what it is. Okay. Okay, so you have a Haar random unitary V acting on SK. So you get the vector as input, you apply the V. Okay, and then you divide the output registers into two equal parts. Okay, so RB and RC. So these are the first half. So basically qubits index from, so that is qubits 1 to lambda by 2, and this is the second half. Qubits lambda by 2 plus 1 all the way to lambda, right? Okay. And then what do you send to the splitting, like to B and C? So you send RB and a description of V. Okay, here you send RC and again the description of V, and they obviously get the secret key in addition to this. B measures the POVM pi B0 pi B1. Okay, obtains or to obtain little b sub capital B, and that's the output. Okay, and C does the same thing, measures pi C0 pi C1 to get B sub C and outputs B sub C. Okay?
What are these POVs?
Exactly, good question. We have not defined them yet. So we will optimize over them. Okay, so we will write down the success probability of such a construction, and we'll say let's optimize over all possible measurements. Since we are unbounded, we can do it. It's not well, even if you were bounded, you probably could do it, but it's okay. All right. So that's the attack. Intuitively, what is happening is whatever ciphertext you're getting, you're just randomizing it. So you got some vector which was supposed to be from some distribution. You just randomize it, send one half to one party, one half to the other party, and they're going to make some measurements. And the point is that because of this statement, intuitively, that if you get half the vector, right, as long as these guys are independently chosen, you'll be able to tell whether you're closer to row 1 or to row 2. That's the intuition. So that's where the indistinguishability is going to come from. Okay, so you started with some ciphertext, doesn't matter what distribution it had, you applied some v, so now it's random. Okay, so now it has a form like this, and you know that because some works still has to be done, right, because they're orthogonal because they can be decrypted. Here there's no orthogonality condition, so we'll have to do a little bit of work, but that's roughly the idea. Okay.
So if they can distinguish, then how do I conclude from here?
Oh, so then so BB can correlate the answer to little b, because little b is the challenger chooses b, right, here, and encrypts USK of either zeros, right. So this is what the ciphertext is.
So how will it correlate?
Yeah, we'll see. Basically, the point is that you either have this vector, or you have either it's 0 or 1, and you have these two vectors, and you want to be able to distinguish them. And the point is that if I give you only half the vector, right, by first applying a random unitary, then just from half that vector you can tell whether I gave it to you from 0, 0, 0 or 0, 0, 1, because it's like this. So whether you were given psi 1 or psi 2, right, you can distinguish them between the two cases. So whether you're given row 2 itself or you're given row 1, so you'll be given the description of psi 1, psi 2, and you're given one row, and you have to figure whether it's row 1 or row 2. That's the intuition. Okay, we'll form this.
Like, so I can distinguish row 1 and row 2, but I wanted to distinguish psi 1 and psi 2, right?
Mm-hmm.
And the trace distance between psi 1 and psi 2 is greater than, okay, so this is psi 1.
Yeah. So just how much you can. So there is like some measurement that will distinguish it. Yeah.
What are those measurements the engineer do?
Yeah. So we didn't define those measurements. So what we'll do is we will write down the success probability of a general scheme like this, and then we'll say you pick the maximum, the POVM that maximizes your success probability. So we'll get it from the optimization. Okay. So let's do the.
This one like more than the previous protocol.
Oh, this is not a protocol. Yeah, this is just breaking the impossibility. Yeah, but it's fun, right? Because it has all these.
This is more information theoretic for my taste.
Yeah, it is fully information theoretic. Like there's no challenger. Yeah, there are no computational assumptions. So that's what they're saying, that if you want to build it information theoretically, you will have these obstacles. Okay. So now here's a little claim. It says that okay. So the success probability, assuming you have some, some POVMs fixed. So success probability of this attack is the same as that of the following. Okay, one small thing which I forgot to mention is that, I said you send a description of V, but V can be, it's a continuous variable, right? So it can be a bit complicated, but you can like discretize it to whatever precision you want. because at the end of it we'll show you have constant success probability. So you can tolerate, you can fix an epsilon small enough so that it allows you to preserve the success probability to be greater than half.
Yes,
Yeah.
and so this is hard random unitary, right? So it's usually very inefficient to give description of, right?
Yeah, of course. The whole thing is inefficient. That's why I said unbounded adversaries. Yeah.
Doesn't matter.
Yeah. This is the. So that's what they are saying, that you either need computational assumptions, even if you want to do it in the plane, if you want to do it in the plane model without any, without the random oracle and so on. So you either need computational assumptions, or you need to have some kind of channels instead of unitaries. So you're throwing away some information. It's not clear how it would work. Okay. So now definition 3.6. So this is the alternate construction. Okay, so you let lambda be a natural number, okay, and you consider the following game between a challenger and consider the following game between a challenger and PC. So we remove A basically. Okay, so there's only these two parties to worry about. What does the challenger do? The challenger samples phi 0, phi 1 from the distribution mu n such that phi 0, phi 1 is 0. Okay. Then you sample a B from 0, 1, divide phi B, so one of these vectors, right, into two parts, right, as before. So there's RB and RC. So this is qubits from 1 to lambda by 2. These are qubits from lambda by 2 plus 1 to lambda. Okay, and then finally you have a description phi 0, phi 1. It's just shorthand for the description of the vector phi 0, okay, and the description of the vector phi 1. So by description I just mean classical description. Okay.
And you are using lambda and interchangeably, right?
Huh?
You sampled n qubit phi 0, phi 1.
Huh.
So n and lambda same for you.
Yeah, that's for, let's put all the mumbo jumbos here. I'm using them interchangeably, but you should take lambda to be, it will also work if n is not the same as lambda, the argument, because n is the length of the message and lambda is the size of the ciphertext, for example, or the security parameter.
And also when you impose the condition that phi 0, phi 1 are orthogonal, so that will change the measure, right? Because if you do uniformly sample, then there will not be any guarantee.
Yeah, that's why it's constrained. You can sample and then put a constraint, so you can.
That will change the probability.
Yeah, I mean this is standard, right? You can always. But I agree. Of course, it's not the same as uniform without any constraints. Okay. So we have this. So that's what the challenger is doing. Okay, and now the challenger will send the description of okay, so you see what's happening. So instead of sending the description of the unitary, right, the description of the vectors is being sent. Okay, and initially you receive the vector from the adversary, right, or sorry, from the challenger, and you split it into two. Now you sample it yourself and then you split it. And the adversary B does the same thing. It just measures pi B0, pi B1, gets B sub capital B. Okay? And C does the same thing. Measures pi C0, pi C1, gets B sub C. Okay, and then you output B sub C, and this outputs B sub capital B. And then you output accept if BB equals BC equals B, reject otherwise, right? Okay, and then you output out. Okay, so what's the key difference you see between these two games? Like, there's one very important difference. So I pointed out the similarities. Any So, how would you prove that whatever an adversary, a pair of adversaries BC could do here, they could also do here? That's not the right way to say it. No? Right. There's lots of differences. That is true. There's no encryption, yes. But intuitively, what phi 0 and phi 1 are doing is basically this, right? So this is basically just phi b in a way, right? And so you can think of phi b essentially as, right? If you look at the way the challenge is set up there, and right? Description. Yeah. This is just something like just as we had description of V, I just got lazy, sorry. Yeah? And what other difference do you guys see? So what about the amount of information B is receiving, for example? So the B in the attack scheme, right, over there, gets a description of V, right, and obviously the scheme is publicly known, right. It gives you the entries of the vectors, classically.
Here, in this case, you are directly giving description phi 0, phi 1 means you are telling the B and C what are phi 1 and phi 0 and phi 1.
Yeah, the description, yeah. So this is a quantum register. RB is a quantum register. There's a difference, right, between having a quantum register versus giving the description of the state. Classical. So classical description is just saying like what is every entry of the vector. Right? Because if I give you a classical description of vector, you can make as many copies. If I give you a quantum state corresponding to the vector, it's not clear, right, that you can make copies and so on. So that's the distinction. Okay. So one key difference is that there's the secret key, right? B and C are getting the secret key. There's no secret key here at all, right? And the reason is that so the secret key basically all that it does, it basically helps the adversary, if you want, to learn USK, right? That's the best it can do as far as the problem is concerned. And it already has a description of V, right? So it has a description of V, correct? Oh shoot, yeah, this is supposed to be V times this because that's hard. Sorry, has a description of V, right? It knows SK, U is publicly known because it's an encryption scheme, right? And then it knows that either 00% or 000% or 001%, right? So it knows that the vector it's getting, it can actually compute that it's either this vector with 0 or with 1, okay? And now instead of going through the SK and from the description of V, you're essentially given 5051 directly, which are just directly distributed from a random distribution. Okay, so the distributions essentially match, and therefore what B and C see are exactly the same. Okay. Okay. Good. Yeah. So we still have this little thing that you're using the spherical measure here, and here the unitary is a high random unitary. So we will have to use one of the lemmas to do the formal proof. Well, that is the connection. Oh no. Okay. So we haven't yet said how the measurements are chosen. So let's do the following. Okay. So the success probability of the game in definition 3.6 in terms of phi 0 and phi 1 can be written as follows. Okay, so we have G phi 0 phi 1, okay, defined to be the max over pi b 0, pi b 1, pi c 0 and pi c 1, and half. Yeah, what do you think the expression should be now?
They want to distribute.
Hmm.
So that will be half plus trace distance kind of.
Uh-huh. So, okay, so what do we want? We want to say that when the answer is, when B is 0, right, they both answer with pi B 0 and pi C 0, right? This is the outcome they get. So with half probability, you will be given the state phi 0, right? And the probability with which you would give the correct answer is what? Right? Tensor pi C 0, phi 0, right? So with half probability you got this state, and with half probability you'll get, right? Good. Okay, and then we have the constraint that these guys are actually measurements, right? So we need to say that P0 P, they add to identity, right? Pi 0c plus pi 1c, and they're positive. So pi 0.
Just write that POV is good enough.
Yeah, that's true. Okay, it's for all I.
But this maximization you can solve, right? This is exactly half plus trace distance.
Yeah. So this you can certainly solve. But the key point is that you can actually learn the argument. Like you can, that's what I said. Right? I hadn't specified the POVM, but now you can learn the you can, given the description of phi 0 phi 1, right? Because you are given the description of phi 0 phi 1, BNC can run this optimization, because they're unbounded, and figure out what the best measurement to make is, and then make that measurement. Okay? I mean, it's crucial that they have the description of 5051.
So they are applying, so this is a vector, classical vector, this description.
Yeah, the description is just a
And
classical
this
vector.
POVM acts as a matrix on,
On the register, no.
oh, P0 acts on that.
So they use the description to solve this problem just on their classical computer, okay? And they will get what the description of these measurements is. Then in the laboratory, they are holding register RB and RC respectively. And then from this description, they will apply that measurement on register RB and RC respectively. Is that clear? No.
No, classically, how are they? This expression is quantum.
Yeah, but you can run it on a classical computer because you know the description of these vectors. It'll take exponential time, but you can run it.
Yeah, then you need pi0 as matrices.
Yeah, you'll get pi0, pi1 as matrices, some giant matrices, and then you run your quantum computer to make the measurements corresponding to pi0, pi1 on the
I'm
input.
a little confused that how this problem is different than just the state distinguishability problem. So you are given two vectors and you want to distinguish them. You will hypothesize using two POVMs.
Yeah, it's identical. I don't think there's any difference.
The only difference is there is only one party who is trying to distinguish. Here there are two parties that are trying to distinguish.
The difference comes from the structure, yeah. So the fact, we have some assumptions about how 5051 appear, this, that, so it will come from there. But you're right, otherwise it's just a distinguishability problem. There's nothing, you're right.
So both B and C will independently optimize over this function?
Yes, but they will get,
The same.
will they get different answers?
No.
Okay. Right? Okay, and
It was like the optimal way of splitting it. Like A could have given B some more qubits, right?
yeah, but we're trying to match this game, right? So in this game itself, you could probably do that, but then you would need this 1/4 plus 1/pi kind of lemma, but for a different split somehow.
Yeah, and that will be bad for you. You will
That-
get 0 then. If you give an even number of,
Yeah, so one party might succeed more. Maybe it gives you some advantage. I don't know what the trade-off is. Maybe like if you give a few more qubits to one, maybe they
but
succeed.
you will win only if both are correct, right?
That is true, yeah. So if one gets worse, it doesn't help, even if the other gets better.
It's an attack we can pick.
Maybe. You can, yeah. You just have to prove it. That's what I was saying. That I don't know how, like this is the technical step that they're using, and I don't know how that would generalize. So it's certainly possible.
Anyway, one attack is good enough, right?
Yeah,
Because
one
we're
attack.
proving.
Yeah, an attack it just says that like the way you want to generalize it is not by constructing. Maybe you could get better asymptotics, but I don't think that's very
That, yeah,
illuminating. What you want is to generalize against a larger class of encryption schemes, which is the main open question. Yeah. Okay, so this we can write as BC win, given that 50 and 51 were used, right? That's the expression. I have 10 minutes, right? 11 minutes, whatever. Okay, good, very good. I don't know, today the chalk is going in my mouth for some reason, some weird taste. All right, so now, okay, so the success probability of the game in definition 6, 3.6 is, this was conditional, right? So now you can just say BC wins, and you can take expectation over 5051, right? Sample from UN such that 5051 is 0, and you run this expression, correct? So you just take basically the average of this expression. Okay, so let's call this star. Okay, NB3 not tip 1, something like that. Okay, So it's actually not hard to see that the success probability of the attack against the indistinguishability, unclonable indistinguishability so this one, right? So far I've made statements about this game. So about that one, we have that expectation over the secret key. So expectation V, remember, was what we said. It's a hard random unitary. V acting on USK 0 0. V acting on USK. Okay. Is this okay? Right, because we argued that they're essentially the same, right? There's not much of a difference, and the only difference is that instead of being given these vectors chosen from the unit sphere, you're given vectors that are encrypted, but then you also multiplied it with V. Okay. And even though, remember, there was this SK, right? So you could imagine that SK does something, but it really doesn't, because as far as the construction of pi B and pi C is concerned, they have the same information. Doesn't really change. This is the information theoretically, it's fine. And so then finally, NB4 says what? NB4 says that, it says star is the same as star star. So basically these two things are identical using which lemma? It's using lemma 3.3. Okay, the one that was relating the Haar measure to the spherical measure that we wrote down. Okay, because that's the only difference. So you're taking expectations over the uniform spherical measure. Here you're taking it over the Haar measure. And
this expectation over SK, this does nothing?
Yeah, so basically for every SK, I think the expression is identical. It doesn't make a difference. So you could.
They didn't use the information from SK?
Huh?
Here, we didn't use SK anywhere in the attack.
Yeah, but like how do you compute pi, right? So this pi B, pi C, the way it was computed, that's what I was trying to argue earlier, right? That so to compute pi 0, pi 1, right, we needed to know these vectors, right? Phi 0, phi 1, the classical description of these vectors. And the classical description of these vectors is that you have the V, right, and U sub U is known, right, because it's a public scheme, and SK, so U sub SK, you can multiply it with V. So you have and obviously whether what 0 0 and 0 1 is, so you can learn the two vectors, the classical description, so you can run the optimization. So whatever you're doing here, you can do exactly. So I mean, these are equivalent in that sense. It's not super formal, okay, I agree. This paper is not like ultra formally written, but I think the ideas are still clear. You can formalize it a bit more if you want. Okay. Okay, good. So we have 5 more minutes, and I think we can maybe do one little more page. Okay, so this is fine. These two expressions are fine, and this is what we'll work with now. Okay, and now what we're going to do is we're going to so we lower bound. That's what. Okay, so star was this expression here. So we're going to lower bound this expression now. Okay. These are shorthand, okay? Shorthand for the POVMs that we looked at. Okay. So we're going to write probability that BC wins or BC win given phi 0, phi 1 as maximization of pi b, pi c, probability b sub b matches little b, okay, and b sub c also matches little b, given that the measurements for pi b, pi c, and the state was phi 0, phi 1. Okay, so far I'm writing it just in terms of the output random variables as opposed to what we were doing earlier. And this is going to be 1 minus you minimize over pi b probability that b sub b is not equal to little b given you measured pi b phi 0, phi 1. Okay, minus minimize over pi c probability bc is not the same as b given pi c was measured and you had phi 0, phi 1, right? And why is this? This is using the following observation. It's a probability A and B happen. It's going to be at least 1 minus probability A doesn't happen minus probability B doesn't happen. Right? You can, it's just a union bound, right? So if this is A, this is B. The probability that both of them happen, right, is going to be at least you take the whole thing, you remove part away and outside away and outside of B. So it will give you the, okay? Okay, I admit the picture didn't help much, but yeah, you can check. Yeah, you just have to write down the intersection and stuff clearly, and then you drop some terms. It'll be fine. Okay. Okay, and then what we can do is we can actually write this, and I'll skip some details because we're a little bit short on time. So one can write this as trace distance rho 0b, rho 1b minus half of 1 minus trace distance rho 0c, rho 1c. Okay. So this I leave as an exercise. Okay. It's an elementary exercise. I'll add it to the notes, the assignment, as a free exercise. Sorry, free points. Okay. Rho 0c, rho 0, rho 1c. Okay. So you see, we're getting quite close. We're in that form where, there's trace distance between rho 0, rho 1. Rho 0, rho 1 are what? They're the half of the thing, and it's the rows are coming from these vectors, and the vectors were sampled. So we're getting close to what we need. Okay, so we'll continue from here next time. Yeah, I think let's stop here today. Otherwise, it'll take too long.